Suppose your friend told you they were an expert in funology. Now, this isn't a word you'll find in the dictionary, but because it combines the word fun with the suffix ology, you'd be able to extrapolate the meaning and that they were trying to tell you they were an expert in making things enjoyable. Or suppose your friend told you they were going to flavorize a bland soup. Again, not a real word, but you'd be able to figure out they were telling you they were able to make their soup tasty. Or finally, let's suppose they told you they were going to chillify your party by dimming the lights and playing smooth jazz. Again, you'd be able to understand they were trying to make the ambiance more relaxed. What all these examples have in common is that even though they're made up words, you're able to figure them out thanks to what linguists call morphemes. These are subword units that contain meaning. And it turns out when you're busy typing away into a large language model like Chat GPT, it's actually using a similar set of clues to figure out what you're saying as well. And that's the subject of today's video on tokenization and byte pair encoding. Welcome to Spreadsheets Are All You Need. If you're just joining us, Spreadsheets Are All You Need is a series of tutorials on how modern artificial intelligence works through the lens of a spreadsheet. That's right. If you can read a spreadsheet, you can understand modern AI. That's because this spreadsheet that you see here, which you can download on the website, actually implements a large language model, all the way from a prompt to getting a predicted token out. In fact, it doesn't just implement any large language model, it implements the entire GPT-2 architecture, an early precursor to Chat GPT that was state-of-the-art just a few years ago. Now, for the purpose of today's episode, the problem we're trying to wrestle with is if you take a look at this spreadsheet, or if you look at the internals of GPT-2, what you'll notice is, sure, we're typing in text here, but as we go deeper into the implementation, you'll just see table after table after table of numbers. In essence, the transformer architecture that's at the heart of GPT-2 only understands numbers. But you're inputting text. So what we need is a process that can convert text into numbers. There's two steps to that. And in this video, we're going to talk about the first step, what's known as tokenization. When I introduced tokenization in a previous video, I used this example. Mike is quick, period, he moves, and showed how it was broken into separate words. But tokenization doesn't just break a sentence into its words. It's not uncommon for a single word to be broken into 1, 2, 3, or more separate tokens. Let's see this in action in the spreadsheet. So here, this tab, type prompt here, is where we enter our prompt with each word or punctuation on a separate line. And note that we have to add the spaces in here manually. And then prompt to tokens is where that text gets broken out into separate tokens, as you can see here. Mike is quick, period, he moves. And underneath, we'll see the token ID. Now, for now, just think of the token ID as its position inside the dictionary of known tokens. We'll be talking more about that in later videos. For now, let's just try some of the examples we used in the introduction to see tokenization for more complex words. Like, I will flavorize the soup. And then because this is such a large spreadsheet, remember that we've got manual calculation turned on. So to calculate, we need to actually hit this calculate sheet button and then just wait a little bit. Okay, here you can see the word flavorize has been broken into two parts, the suffix IZE, as well as the word flavor with the space in front of it. Let's try one more example. Let us chillify the party. And again, you see chillify has been broken into the suffix ify along with the word chill. Now, byte pair encoding isn't always perfect. So let's talk about an example here where it fails. The brace will prevent re-injury. Now, to you and I, re-injury is the word injury with prefix RE in front of it. But as you see here in byte pair encoding, it's actually broken into the word REIN and then the word jury. So It doesn't always line up with, a native English speaker expectation, but it does do a good job of actually capturing the most common subword units that tend to have meaning. Now, you're probably wondering why we don't just turn words into numbers by just assigning each word a number, like dog as 1, cat as 2, and so forth, throughout the entire dictionary. Well, this has a couple problems. The first is that this isn't able to handle unknown or misspelled words, which are actually really common if you're, say, scraping all the text on the internet. Now, that being said, there are transformer models that do have a special unknown token, so it's not an insurmountable problem. Another problem is just supporting a large vocabulary size increases the size of the model. GPT-2 has about 50,000 tokens, but English has about 3 times that, 170,000 words. And so the end result is that it creates more memory and more compute needed to run and train the model. We can actually demonstrate this inside the spreadsheet. So inside the spreadsheet is a specific tab called model_WTE, what's known as the text embedding matrix. The important thing to know here is that each row of this matrix corresponds to a single word. So it's the entire vocabulary size pi, in this case 50,257, because there are 50,257 known tokens inside the GPT-2 model. Now, the width of this matrix is something called the embedding dimension. We'll learn about that in later videos. For now, just know it's about 760 columns. The key point is that the entire GPT-2 model we're playing with is 124 million parameters. If we were to take this matrix and add 120,000 more rows, effectively what we would need to have all the words in the English language in a word style embedding, we're basically actually nearly doubling the number of parameters to 216 million. That's a huge increase in the amount of compute needed just to calculate a token. Let's go see this in the spreadsheet. So here we are in the sheet. And if you look at the list of all the tabs in this workbook, you'll notice there's a large number of them that start with model underscore. And these are basically tables of numbers like this. And when somebody talks to you about the number of parameters in a model, it's really basically how many numbers are in every single one of these tabs across this entire model. And in this case, in the spreadsheet, there's 124 million of them. Now, the model we were talking about before, or rather the matrix we were talking about before, is this matrix, WT. And here you can see it's got 768 columns and it's got 50,257 rows. Each of these rows corresponds to a single token. So let's do some calculations here. Create a blank workbook. So we know that the original matrix height is 50,257. We know that the original matrix width is 768. If we were going to add enough rows to accommodate all the words in the English language in a word style tokenization, then we would need additional rows. We know that's 170,000. So actually that's the total rows for word encoding, tokenization, I should say. That means the additional rows is this minus that is about 120,000. So let's add how many additional parameters that would be. Well, that's additional parameters are just simply the number of additional rows times the width of each row. That's 768. Let's expand this out so it's easier to see. And then let's add some commas so it's easier to read. And let's get rid of those extra arrows, or sorry, zeros rather. And then remember that the entire model is about 124. So this is the original model size. So basically, we're nearly doubling the size of the model. We're adding 91 million more parameters just to accommodate all the words in the English language. Using byte pair encoding, we can do this all a lot more flexibly and using only 50,000 tokens. Now, you might be wondering, why don't we go the other way? Let's use character-based tokenization. So give each letter a number. So A equals 1, B equals 2. And at least in the English language, there aren't that many characters, so you're not going to have that many rows. And if you're familiar with the ASCII encoding, or you come from a developer background, you're probably used to this kind of setup as well. This has its own couple of problems. So the first one is it actually creates longer sequences. Let me show you that. Let's close this. And let's go to where we enter in our prompt right here. After we've turned the prompt into tokens, those tokens are then turned into what are called embeddings. These are long vectors. Each of these tokens goes into a row of 768 values. The key point, though, is that this matrix here, this is basically what you're probably familiar with as the context link when you type into something like Chat GPT, is as long as the number of tokens. Right now, you can see it's only about 6 tokens long. But if each of these were split out by its character, it's going to be a lot longer. So our context link that we have to process for something that's only, in this case, 6 words long is going to be a lot longer. And this gets carried through, this length of 6 gets carried through not just here, but through actually every stage and every layer of the entire transformer pipeline. So in effect, even though with the character-based tokenization, the size of the model, that WT matrix, may be smaller, the length of the context window in order to process the same amount of text gets longer through the entire inference and training pass. That means, again, more memory and more compute. There's another problem that's more subtle, which is that there's low semantic correlation of characters themselves. So as an example of this, you've probably seen this email that went around a couple years ago, and they've jumbled all the letters in the words, but it's still readable. So the first sentence basically says, according to research at Cambridge University, doesn't matter what order the letters in a word are, the only important thing is that the first and last letter be in the right place. By the way, that's technically not true, that the first and last letter need to be in the right place, but the point still stands that the meaning of a word isn't conveyed in just the characters itself, but in how they're grouped together. And because the characters themselves don't carry that information, that puts more work on the training algorithm to learn English and what the meanings of words are than it would if it was actually using words to begin with. In the end, both these problems mean more memory, more compute. It becomes harder to train and use the model. So if character tokenization has its own problems and word tokenization at the other end has another set of problems, maybe there's a Goldilocks in between the too small, too big that's just right. And it turns out there is, and that is subword tokenization. Now, there's more than one subword tokenization algorithm out there. The one that GPT-2 uses is called Byte Pair Encoding, or BPE, and it's got 2 phases. The first phase is a learning word, where it learns what the common subwords are in a particular language. And then the second phase is the actual tokenization phase that takes input and turns it into tokens to be processed by the large language model. So for the first phase, I want you to imagine you've gathered a large body of text, maybe by scraping all the English language on the internet. This is sometimes referred to as a corpus of text. And you pass that into the BPE learning algorithm, which turns this into a known vocabulary of tokens. And we'll walk through this in a little more detail in the next few slides. Then in the tokenization phase, we take the input from the user and we combine it with the vocabulary that we got from the first phase to output tokens that are then used in later processing stages of the model. I'm going to illustrate the learning phase through some slides and then implement the tokenization phase inside the sheet so you can see how it actually works. To show the learning phase, I'm actually going to use the same example that was used in this paper that introduced this algorithm to machine learning. And it's a short, readable paper. It actually has a Python script in it. If you want to try it out, I'll just run through it in slides here for now. Now, I want you to imagine the part on the left, the corpus, is the result of maybe scanning all the English language we could find on the internet. Obviously, it's not that long. It's a toy example to illustrate the process. And it just has, in this case, 5 words. The word low occurring 5 times in our scan, the word lower occurring twice, the word newest occurring 6 times, and the word widest occurring 3 times. And then we'll start on the right with our vocab of just the characters from A to Z. Now, in order to make the process more clear, we're going to rewrite the corpus a little bit. I'll use the dot symbol to show the separation between the individual characters. I'll use this underscore character to illustrate the boundary of where a word ends and another one might begin. The first step in learning the vocabulary is to look at all the adjacent pairs of characters and count up which one is the most frequently occurring. So for example, the letter E next to the letter S occurs 9 times. It occurs 6 times in the word newest, and it occurs 3 times in the word widest. So it occurs a total of 9 times. So we then write down E paired with S with a frequency of 9. And then we do this for all the adjacent pairs of characters inside our corpus. And then we look at the one that has the most frequent occurrence. In this case, it's E and S, although we could pick S and T or T in the end of word character. They all have 9. And then we take that and we add that to our vocabulary. We then reprocess our corpus with our new vocabulary. We take all occurrences of E paired with S, and we transform them into a new ES character. So now ES together are going to be treated as if they were a single character, even though to us, they're considered separate characters. Then we repeat the process. So now the most frequently occurring pair is this new ES with the T character, and that occurs 9 times. We then add this to our vocabulary below the newly added vocabulary entry from the previous pass. So now we have a vocab that's E paired with S, and then ES paired with T. And again, we reprocess our corpus such that ES paired with T is now treated as a single subword unit, EST. And this is what we have after 2 passes. We have a vocabulary of 2 new subword units, E and S, and then EST. And then we have our corpus that's been tokenized into our vocabulary. After multiple passes of this process, in this case, after 10 passes, we have something like shown here. We have a vocabulary, which has 10 tokens, the number of tokens equal to the number of passes we did of the algorithm. And then on the left, our corpus that's been segmented and tokenized according to this new vocabulary. So note the most frequent words in our corpus, low and newest, were actually tokenized into their own individual words. Meanwhile, lower and widest were broken into separate tokens. But you'll notice that BPE has already started to learn some of those morphemes we talked about earlier. In the case of lower and low, it's understood that they both use the same subword unit low. And in the case of EST, in newest and widest, it's understood that morpheme and recognized that as well as its own independent token. While the BPE learning algorithm is actually fairly simple, it may take rewatching this a few times to get an intuition for how it works, or you can run the Python program I showed earlier and get an even better feel for how it works. Now let's see how tokenization process, that phase 2 of the algorithm, works in detail inside the spreadsheet. Before we get to the spreadsheet, I want to show you this file. This is the vocab.bpe file. You can get this from OpenAI when you download the full weights of GPT-2. You'll notice there's 50,000 tokens, and these are the merges that we saw earlier, where there's a space character between the left and the right. You're seeing a dot right there, but that's because of my text editor. In the actual text, it's really just a space. And then as a result, to represent the space character itself, you see this special kind of G with an accent on it. That's actually the real space character. We have to substitute that out. I've gone ahead and actually done that inside the spreadsheet. So that special G character has been replaced with a true space. What we have here is the left half of a pair, and in column 2, the right half of a pair. I've added 2 new columns. One is called the rank, so we can understand which pair or merge has the highest priority in the parsing, and score, which is the inverse of rank, just to make the math and calculations and formulas a little easier. It's easier to find the max and use 0 to represent when there is no match. Now let's go to where the parsing and tokenization takes place. That's again in this sheet, prompt to tokens. Now, this sheet's a little complex. So what I'm going to do is I'm going to create a new sheet that builds up to the same process that you see here. Let's insert a new sheet and let's use an input word. So let's use input word Let's use Chillify, for example. Actually, let's use Flavorize. And note that I've used space, then the word Flavorize, because in GPT-2's algorithm, the tokens start with the space character rather than having that end of word character that I showed in the previous example. Now let's actually break this into characters. Input characters. And I'm going to use a number to indicate which pass we're at. And then I'm going to take this and I'm going to split it into characters. Now you notice I'm using the split into characters function. That's not a normal Excel function. If you go to the name manager, you'll see this is really just a named function. And you can actually see the implementation of it right here, split into characters. Now we're going to create all the possible pairs, all the possible adjacent pairs. So that would be this, which is the space character, concatenated with that F. Let's move that one over. And then if I hit calculate sheet, you can see the result here. So here we have space with F as a possible pair. We have F with L as a possible pair, L with A, and so forth. I'm going to actually put this and mark this as our end. So let's do that. Let's format these cells and let's put a border here so we can see where the end is. We want to be able to handle blanks properly. So next up, we want to understand what the score of each of these possible pairs are inside our vocabulary. So let's get the score. And I will put a question mark there. I'll save that for Booleans. So for this, I have, again, a named function that really is just implementing a standard filter function with a little protection around it for if something doesn't match. And we'll input the left character and then the right character in a pair to get its score. So this space with an F has a score of 49979. We can then do that across the entire sequence. Let's hit calculate sheet again. And then we can see the scores of each of the possible pairs. Now we need to figure out which of these pairs has the highest score. So let's extract the max score out of this range. So this is going to be max, and we're going to take the previous row, and we'll go from column 2 all the way to previous row and column 12. And hit calculate sheet, and these should all match up. There we go. Now we want to see which one has the max score. So is max score, and we'll make this a Boolean. And that's simply saying, is this max score equal to the score for this pair? So this one is obviously false. And then let's carry this formula through. Hit calculate sheet. And here we can see the max score is 49983, which is the pair OR. So what we want to do for our output is say if it's the max score, then take the pair. Otherwise, just carry down the original character that was in the input. Let's carry that through. Paste that, and then calculate sheet. Okay, here we see of these columns, only the one with the maximum one, OR pair, which had the highest rank, gets carried through into our next version of Flavorize. Now, there's a little problem. Actually, there's two problems. The first is you'll notice that we carried through this blank character. So one way you can fix that is look for blanks and then make sure they don't get propagated down. The second problem you'll notice is a little more subtle, and it's that because R was used in OR, we now need to make sure that this character doesn't get propagated down either and leaves an empty space right here. We're going to add 2 new rows. The first one is going to be is input blank. And then the second is going to be is previous sibling maxed. So let's solve this blank one first. So all we have to do here is just check if the input character itself is empty. And we'll propagate that over. And here you can see in the last column, it's true, indicating that that one is blank. And then for solving this R getting propagated down, even though it was part of OR, all we have to do is check if the previous sibling was the max column. And that all we have to do is just check max score, which is this row right here. Just propagate that value over. And here at the very first column, there's no previous sibling, so it's always false. Now let's calculate the sheet. And here we can see the column with R now has a true here, which is going to let us know that this field right here or cell needs to be blank. So we're going to change our output formula to now check if the previous sibling is at max score or the input character itself was blank. In that case, we just return an empty result. Otherwise, if this column is the max score for this pass, then we take the pair. Otherwise, we take the original input character and propagate that through. And propagate this through. And calculate sheet. Okay. So here we can see in this case where there was no input, we get a blank here as expected. And in this case where the R has been moved over into this pair OR, which got merged down, that column is now blank as well. So now let's show what the next pass is going to do. And we'll use a formula so we can keep track of which pass we're on. This is our second pass. And the input for this pass is going to be the output right here of the previous pass, but we're going to remove any blanks that are sitting in between these characters. And to do that, I'm going to use another special function, get non-blanks in range. And this function you can find, again, by going into the name manager. You'll see it in here. It's really just a simple version of filter with some error checking on it and removing any blank characters, or rather blank spaces and cells in the range. So here we've got flavorize with this blank removed. And now we're just going to repeat the same process we did before. So take this row, copy that, and paste it down. And now we rerun the algorithm. And here we can see in the second pass, the highest scoring pair was the first one. That's the space character with the letter F, and that got propagated down and left a empty cell here, and the rest of them came down as normal. Now at this point, we can just copy all these rows and just continue repeating through the spreadsheet. So that's another pass. And then we'll go down some more. And that'll be another pass. Yep. Down one more. There we go. Then right here. And we keep going. Now, because we have 10 characters, we're basically going to need about 9 passes, one less than the number of characters in the word itself. That should be enough. Let's calculate the sheet. Okay, here you can see flavorize has finally been broken down into the word flavor with a space in front of it and the suffix IZE. Let me point out a few things here. You'll notice that basically around the 8th pass or so, it had already figured out what the right tokenization was, and it was just propagating it through the next few phases. You'll also notice that some of these possible pairs, like this one right here, which is AVOR with IZE, those two put together, has no score. That's because that token simply does not exist in the vocabulary for GPT-2's byte pair encoding, so it ends up as a blank. The other thing that's worth pointing out is that how this would be different from, say, naive string matching and just looking for a particular set of characters. So here, let's take IZE here. If I change this word to, say, Eisenberg and run the sheet again, you'll notice that the final tokenization is a lot different. We don't break out IZE together. In fact, it's I, Zen, and Berg. And that's because of how the byte pair encoding tokenization algorithm is working by prioritizing certain sets of morphemes, or rather subword units, over others when it tokenizes the word into its different pieces. Okay, so that's in essence the algorithm for how byte pair encoding works. Now, you'll notice that prompt to tokens is laid out a little bit differently. It's got a bit different formulas that help it work across multiple words. So you'll notice there's multiple words here, and it's got formulas that try to take into account the position of the cell using modulo arithmetic to make copy and pasting across the columns work a lot easier. But in essence, the algorithm implementation works roughly the same as I've outlined in this sheet here. Okay, now that you've seen the learning and the tokenization algorithms for byte pair encoding, I just want to wrap up with a few caveats. And the first is that byte pair encoding is not a universal good. It has its own trade-offs. And this post from Andrei Karpathy highlights some of those problems. One of those is this effect called solid gold Magikarp. And the effect is if you ask one of these large language models to repeat back certain tokens, in this case, StreamerBot, it responds back with, "You're a jerk." Or if you ask it to repeat back this string, it responds with, "You are not a robot," or "You are a banana." My favorite example of this is if you ask how many letters are in this username, it can't repeat that string back to you. Now, part of the problem here really isn't byte pair encoding itself. It's the fact that there's a learning algorithm for byte pair encoding, and then there's a separate learning algorithm for the rest of the large language model. And what has happened is, in this case, this David JL is a very prolific user name on Reddit. And that particular user occurs so often that it got learned by the tokenization algorithm. But it occurs so infrequently in the rest of the training data across the rest of the internet that it has a very low probability of ever being output as an output token. And so you end up with this disconnect between it's in the token space, but it's not in the probabilistic output space. And that creates these kinds of effects where the model is going to give you back some weirdness when you ever use these tokens. Another problem with byte pair encoding is it's very English centric. And there are languages where the fundamental word separation and principles involved in byte pair encoding don't work. There are other encoding schemes. Sentence piece, for example, is one of them, and this is being used for English to Japanese translation. And there are plenty of other tokenization algorithms. The website Hugging Face has a great list and libraries for tokenization that you should take a look at. And then I did say that both character and word-based encoding don't work. There are certainly examples of other transformer architectures that do use these types of tokenization. Here actually is one called Carformer that uses character-based tokenization. And the tokenization learning algorithm actually takes place at the same time as the rest of the machine learning model, which hopefully solves some of the other problems we've just talked about. And then finally, it's worth noting that tokens do not have to be limited to just characters or text. Anything that you can translate to numbers, you can then put through the rest of the machine learning model, whether that's audio or in this case, images. So In this paper, they used patches of an image and turned those into tokens that they then put through the rest of the transformer model. Okay, so that's how tokenization or byte pair encoding works inside the GPT-2 architecture. In future videos, we'll cover the rest of the model with the text and position embeddings up next. Thank you.